very important. Not only important in solving polynomial inequalities and rational inequalities, it's also important when you go to calculus to analyze the behavior of a function, like a concave up, concave down, increase, decrease. So sign chart method is very useful. Let's look at the first problem. This problem is an inequality because we have this inequality symbol. We know the four inequality symbol, right? Bigger than equal to, less than equal to. This is also inequality symbol, but we don't really consider that symbol. And this is a polynomial inequality. This is a polynomial inequality. And this inequality is already in the standard form. The standard form of a polynomial inequality is on the right side, we have 0. On the left side, we have a polynomial, function. So this is a polynomial function. We are going to solve this inequality, all right? Every time we solve a polynomial inequality or rational inequality, the first thing is to rewrite the inequality in the standard form if it's not yet in the standard form. And this problem is already in the standard form, so we are fine. Okay, how do we do that? The way I do it is I firstly make sure the inequality is in the standard form. Right side is 0. And then I let f of x be the function on the left. 5x squared plus 9x minus 2. All right? And then I'm going to try to factor this polynomial function. It is a quadratic trinomial. Let's see how do we factor it. 1, 5, 2, 1. So this would work. 1 times 5 is 5. 2 times -1 is -2. 2 times 5 is 10. 10 minus 1 is 9. So the quadratic trinomial here can be factored as x plus 2 times 5x minus 1. And then I'm going to identify the zeros for the function f of x. F of x has 2 zeros. You can also understand zeros as roots, right? Function f is a quadratic trinomial, quadratic function. We can factor the quadratic function as x plus 2 times 5x minus 1. And then we can see from the factorization, the function has 2 roots or 2 zeros. The 2 zeros are -2 and 1/5. You see it, right? -2 would make the first factor be 0. If you let x be -2, -2 plus 2 is 0. A root or zero of function is a value of x that could make the function be 0. If you're plugging in x equals that value, then the corresponding y value is 0. Y is f of x, right? So -2 is a 0 because if we're plugging in x equals -2, the function equals 0. Similarly, x equals 1/5 is also a 0. 1/5. If we're plugging in x here equals 1/5, 5 times 1/5 is 1. 1 minus 1 is 0. If you don't see it, you can just let this factor 5x minus 1 be 0 and solve the simple equation +1 + 1. We have 5x equals 1. Divide by 5, divide by 5, we have x equals 1/5. So that's how do we find the 2 zeros. All right, and then we can start the chart. And then we're gonna make the chart. You can design the chart, if that whatever the way you feel comfortable. This is how do I design the chart. The first row on my chart is x. We know the function f of x is a polynomial function, so the domain is all real, right? Domain is all real. And the two zeros separate the domain all real into 3 intervals. If I draw the real number line here, this is the domain of the polynomial function. Then let's say -2 is here, 1/5 is here, 1/5 is here. Then the two zeros would separate the domain, the whole domain, into 3 parts or 3 intervals. The first interval from -infinity to -2. Second interval, -2 to 1/5. Third interval from 1/5 to +infinity. Okay, so the first row in my chart, I'm going to have the 3 intervals. How do we get the 3 intervals? We consider we found the two zeros for the polynomial function, and the two zeros separate the domain from -infinity to +infinity into 3 parts, into 3 intervals. So we have a -infinity to -2, and then from -2 to 1/5, and from 1/5 to +infinity. We know for an interval notation, if the endpoint is infinity or -infinity, we use parentheses, right? What about the other endpoint? What if the endpoint is constant? Here, -2, 1/5. Should we use parentheses or use a bracket? And we should look at the original inequality symbol here, right? And we use a bracket in this case because it's bigger than or equal to 0. Bigger than or equal to 0. Okay, so we use bracket. That's the reason. And here's -2 to 1/5, and here's 1/5 to infinity. All right. So that's the first row in the chart. The first column here is x, because x, the independent variable, whose value could fall in this interval, or this interval, or this interval. All right. Okay, so this is one way to design it. Okay, I think this would work. And the next row in the chart, we are going to select a testing point. We are going to select a testing point in each interval. Okay, in each interval, but the endpoints cannot be chosen as testing points. Any point would fine, but the endpoints cannot be the testing point. All right, so the second row, we are going to pick a testing point from each interval. Any point inside the interval is eligible to be the testing point, except the endpoint. You cannot choose the endpoint as the testing point, all right? Any other point is fine. So the first interval from -infinity to -2, which testing point we want to choose? And we will, of course, want to pick a number that is convenient, as convenient as possible. I'm going to pick -10. It has to be a negative number, and 10 is a pretty convenient number. So I pick -10. And the second interval from -2 to 1/5, I'm gonna pick 0, because 0 is inside the interval, right? And the third interval from 1/5 to +infinity, I can pick 1, or I can pick 10, right? Yeah, I think 1 would work, so I'm gonna use 1 here. So that's the second row of the chart. Next, we are going to, I want to make the first column a little bit wider. Next, we are going to have f of x. We are going to have f of x, the function on the left side of the inequality, the polynomial function, in the factored form. Okay. Next, we are going to have f of x in the factored form, which is x plus 2 times 5x minus 1. And we want to determine if the testing point make the function positive or negative. So second row, we have the testing point, right? And the next row, we are going to plug the testing point into the function f to see if we have a positive or negative. So that's what we're trying to figure out. So the first testing point is -10. And we are going to plug -10 into the polynomial function in the factored form. The reason we do the factored form because there's a benefit, okay? Yeah, let me explain why. What's the benefit? I'm going to color the two factors in two different, color. This one is blue, and the other one, maybe let's use yellow. So the function is blue times yellow, and we don't really care the value of the function when x assumes -10. We only care the output of the function when the input is -10, positive or negative. So for that reason, let's consider when we plugging in -10, is the blue part positive or negative? -10 in the blue, -10 plus 2 is going to be negative, right? I don't really need you to tell me is -8. We don't really care about that. We only care is it positive or negative. So -10 would make the blue part negative, right? And it will make the yellow part also negative, correct? So when you're plugging in x equals -10, the blue is negative, the yellow is negative. Would that make the product positive? And please let me know if that's clear.
Yes.
Okay, very good. So it's very quick. This method is very fast because you really don't need to find the exact value of the output. You only need to concern the sign of the function when you plugging in the testing point. The second testing point, the testing point for the second interval is 0. 0 is very convenient. If we plug in x equals 0 in the blue, 0 plus 2 is positive, okay? Yeah, you're gonna remember, you're gonna do some notes on the scratch paper. 0 would make a blue positive, 0 will make a blue positive, 0 would make a yellow negative. So we have a positive times a negative, and here's a negative, right? And the next interval, the testing point is 1. 1 here actually acts as a representative for all other points in the interval. So let's plug in x equals 1. 1 would make the blue positive, will make the yellow positive as well. So positive times positive is a positive. All right. So at this point, the chart is complete. The chart is completed. And we can erase those parts. And we can actually go ahead to make a conclusion. The conclusion is to solve the inequality, right? Polynomial inequality. The problem is to solve the inequality means we need to find values for x such that f of x is bigger than or equal to 0, right? Is bigger than or equal to 0, non-negative. And as you can see, the function f is negative in the interval 92 to 1/5. 0 here is a representative. It is a point in the interval. And the sign of the function at 0 at this representative is the same with the sign of the function in the whole interval, over the whole interval. So this basically tells us we can conclude the function is positive from -infinity to -2. Well, positive or 0, okay? And -2 is a 0. And the function is negative from 92 to 1/5. The function is positive from 1/5 to infinity. So we found the intervals in the domain that would make the function bigger than or equal to 0. So now we can conclude the solution of the inequality in the interval notation is net infinity to 2, because we want a positive bigger than or equal to 0, right? So net infinity to 2 union 1 over 5 to past infinity. And we're done. Do you like this method? Let me summarize, okay? What's the process of applying sign chart method to solve a polynomial inequality? The standard procedure. Firstly, we have to make sure the polynomial inequality is in the standard form. If it's not, you have to modify and rewrite the polynomial inequality in the standard form. In the standard form, right side of the inequality has to be 0. Very, very important. And left side is a polynomial function. And next step is to factor the polynomial function on the left side. It's convenient if you can let y equals the function on the left or f of x as the function on the left. I use fx. I let fx to represent the function on the left side, and I factored it into two factors, two binomial linear factors, x plus 2 and 5x minus 1. From the factorization, we can see the function has 2 zeros. The 2 zeros are -2, 1 over 5. And the 2 zeros separate the whole domain, net infinity to past infinity, into 3 parts, 3 intervals. And so that give us the first row of the chart. The first row are the 3 intervals, and that's where x is going to be, right? Independent variable x would it be in this interval or this one or this one? And the second row, we are going to choose a testing point from each interval. And the testing point cannot be the end point. Has to be a point inside the interval. And we want to pick the testing point as a convenient integer, right? If we can use integer, we don't want to do fraction. And the next row in the chart is to see the value of the function at each testing point. We don't really need to know the exact value. We only need to know is the value of the function positive or negative at those testing points. And those testing points are representative of the interval it is located in. So we can make a conclusion function f is positive from net infinity to -2, open. Negative from -2 to 1/5, open. Positive from 1/5 to past infinity, open. And when we conclude, we need to consider the bar in the inequality symbol. So that's the reason we have bracket here and a bracket here, all right? Is that clear, everyone?
Yes, I understand it.
Okay, very good. And regarding the design of the chart, if we do parentheses here, that is okay. And that is really fine, okay? We can do parentheses here. And sometimes they do this. They add two more columns. They added 2 more columns. So they put one column here, 1 column here. And this column is x equals -2. So if those intervals are open intervals, if you design them as open intervals, then you're gonna have a -2 here in between the 2 intervals, and you're gonna have a 1 over 5 here in between 2 intervals. And we do not apply testing point, and we know function is going to be 0 here and 0 here. If that helps, yeah, this is another way to design the chart. I think this is one more sophisticated, right? Okay, so next question, let's practice more. Question number 2 is also a polynomial inequality. The polynomial inequality is already in a standard form. Right side is 0, left side is a polynomial function. Let f of x be the polynomial function on the left side, which is x squared plus 3x minus 10. You need to be able to quickly and correctly factor any polynomials when you need to in this course. Factoring polynomial is a challenging chapter in Foundation 2, but in pre-cal is a very basic skill, and you will have to be able to get it done very fast. So this one has x plus 5 times x minus 2. Positive 5, negative 2, multiply to negative 10. Positive 5, negative 2, add up to positive 3. So that's the factorization, all right? And from the factorization, we can see f of x has 2 zeros. The 2 zeros are negative 5 and a positive 2. Negative 5 is the opposite of this number. 2 is the opposite of this number. Okay, so now we have our 2 zeros. And then I'm going to draw the real number line to represent the domain of the polynomial function. In the domain, in the real number line, I mark negative 5 and a positive 2, the 2 zeros. And as you can see, the 2 zeros would separate the domain into 3 parts. This interval, second interval, third interval. And now we are ready for our chart, okay? The first row is x. If we use the open interval, then from negative infinity to negative 5, the first interval. And the negative 5 is the 0. Negative 5 is the 0 of the function. I can put an extra column to contain negative 5. That's totally okay. And from negative 5 to 2. Again, it really depends on how do you design the chart. As long as it serves the purpose, you can correctly find the intervals on which the function is less than or equal to 0. That is okay. And we can put a 2 here. And then the last interval, 2 to infinity. All right. And the next, yeah, I forgot this again. I need to put the first column wider. I need to put the first column wider. Okay. Next row is the testing point. Again, any point inside the interval is okay, but cannot be the end point. So from negative infinity to negative 5, I would pick negative 10. From negative 5 to 2, I would pick 0. From 2 to infinity, I would pick 10. Right? You can put 100 if you prefer. Next row is going to be the function f of x in the factored form. In the factored form, x plus 5 times, this is too narrow, is equals x plus 5 times x minus 2. So let's say the first factor is blue, the second factor is yellow. So the function f of x is blue times yellow, okay? In this row, we are going to see the sign of the function f at those testing points. Those testing points are representatives for each interval. Let's see, negative 10, pretty convenient number. Negative 10 would make the blue negative, would make the yellow negative. Negative times negative, you have positive, right? Yeah, at negative 5, the function is 0 because negative 5 is 0, right? It's a root. In the second interval, the testing point is 0. Let's plug in 0. 0 would make the blue positive, would make the yellow negative. So positive times negative is negative, and then the 2 is 0. And the third representative, the testing point is 10. We plug in. Positive 10 would make the blue positive, yellow positive as well, so positive, okay? But in this case, we are looking for intervals. We are looking for intervals such that the function f of x is less than or equal to 0. In previous problem, we are looking for the intervals over which the function is bigger than or equal to 0, right? So in this case, less than or equal to 0. So we are not gonna do this one, not this one, and it's gonna be this part, okay? It's gonna be this part, less than or equal to 0. So it's going to be the interval -5 to, all right? Closed interval, because we are looking for the value of x, the values of x that could make the function less than or equal to 0. In the open interval -5 to, the function is strictly less than 0. At -5 and 2, the function is equal to 0. So less than or equal to 0. So we can combine this part, you know, -5 to positive 2 open interval and 2 as a closed interval, -5 2. So that is the solution. That is the solution. And let me know if that is clear. Do you like this method? Any feedback?
I understand it.
Okay. Thank you for your response. Let's see who is online. Alisa. Oh, Alisa is here. Okay, so those are two polynomial inequalities. Okay, this one is also a polynomial inequalities. The difference is in this polynomial inequalities, the polynomial is more complicated. But good news is, since it's complicated, the question does not require us to factor it. Instead, the question already have the left side factored already. So we let, this is polynomial inequality, we let f of x be the left side, x cubed times x minus 3 times x plus 7. It's not exactly necessary, but I'd like to play the factor like this, if you don't mind. Minus 3 plus 7. And we also have a cube, third power on the first factor. And this way I can easily identify the zeros for the polynomial function. The function, then f of x has how many zeros, guys? How many zeros or roots? You don't really have to worry about the multiplicity. We only consider the multiplicity when we decide the behavior of the graph of the polynomial function. Is that obvious? Ether, how many zeros do we have here for this function?
We have 3 zeros.
Awesome, very good. Exactly, yeah. 3 zeros. Perfect. 3 zeros. And they are, yeah, just take the opposites of the 3 numbers I put in red. Opposite of 0 is still 0. So 0,
3 and minus 7.
Perfect, exactly. Yeah, another reason I like to play this way is that there's a chance sometimes students miss the 0, 0. Means the root 0, because they can easily tell, okay, -3, 3 is a 0. Positive 7, -7 is 0. But there's a chance they forgot there's an x cubed. That means 0 is also a 0. Number 0 is also a 0 of the polynomial function, a root of the polynomial function. Okay, very good. So now I'm going to draw the real number line, the domain of function, polynomial function. It's good to know for any polynomial functions, the domains are real, from net infinity to past infinity. And also when you put the zeros on the real number line, be careful with the order. That if you mess up the order, that's going to be a very simple mistake. But it is a very serious mistake as well. So -7, 0, 3 is here, right? -7 first, and then 0 in the middle, and then 3. And those 3 zeros divide the whole domain into 4 parts. First part, second part, third part, fourth part, all right? I'm gonna put this in the next page. And now we are ready for our chart. Now we are ready for our chart. This time I need to remember enough space for the first column. And first row is x. We have from -infinity to -7, open, and -7 is a 0. From -7 to 0, and 0 is a 0. From 0 to 3, 3 is a 0. And from 3 to past infinity. So we should have 4 intervals, 3 zeros. I can color them differently if that helps. We do, this is the interval, 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 interval. And this is a 0, this is a 0, this is another 0. Okay, second row, testing point. In the interval -infinity to -7, -10, to me, I would do -10. Would be a good testing point, representative. From 97 to 0, from 97 to 0, maybe I would do 91 or 95. Let me do 91. Depends on your preference, okay? Any point is fine. Any point can be the testing point. 91 is okay. 91 is pretty convenient. And from 0 to 3, positive 1. Positive 1 would be the testing point. From 3 to past infinity, I can try 5 or I can try 10, right? All right, next row should be the last one. Is the function f of x in the factored form. Even the function is very complicated, but it's already factored, so that is a good thing. X cubed times x minus 2 times, oh, hold on. Did I miss, oh my gosh, I miss a square here. I miss a square here. Even it doesn't matter, so far doesn't matter, but it was an error, I apologize. Yeah, there's a square here. The degree of the polynomial function is 6. Well, you don't need to know that, but it's good. It's a 6. Okay, it's a square here. So x cubed, x minus 2 squared, and x plus 7. Double check, triple check is very important. X cubed, x minus 2 to the, oh my gosh, x minus 3. X minus 3 to the power of 2. And then x plus 7. Okay. X cubed, x minus 3 to the power of 2, x plus 7. Okay. Even there was an error, but so far, everything gonna stay the same. It doesn't affect yet. Okay, so the function has 3 factors, right? I'm going to color them differently. The first part is blue. Second part is yellow. Be very careful, the square matters. The square matters. And the third part is green. Oh, I already used green. I'm gonna use a different color. Pink. Pink. All right, pink. It's very important the yellow has to be positive, okay? The yellow can never be negative. Be aware the yellow part, since it's a square there, is not possible to be negative, okay? Now let's plug in those testing points. When the testing point is -10, blue, so you can take a note. You can take a note. When x is -10, blue is negative, right? Because the cube, -10 to the power of 3 is -10 times -10 times -10 is going to be negative 1,000. And yellow is positive. You don't have to worry about, because the square always a positive, okay? It's always positive. And pink is a negative. So negative times positive times negative is a positive here. Okay. And now let's do 91. 91. 91 would make a blue negative. 91 times 91 times 91 would make the yellow positive. Again, yellow always positive. Even you plugging in x equals 91, 91 minus 3 is 94. But square of 94 is a positive 16, so it's positive. And it would make the pink positive. This time is positive. 91 plus 7 is 6, positive. Negative times positive times positive is negative. Positive 1. Positive 1 would make blue positive, yellow positive, is always positive yellow, pink positive. Positive times positive times positive here, right? And the x testing point 10 would make the blue positive. Yellow still positive, pink positive. Positive times positive, so positive here, all right? You might make sense of the reason. How come the two intervals next to each other, but the function are both positive? Because 3 is a 0 with multiplicity 2. That means the curve, let's say this is 3. The curve touch 3 and bounce back. That's the reason from 0, this is 0. 0 to 3 is positive, is above the x-axis. But from 3 to positive infinity is still positive. It's still above the x-axis. I hope you see this. It's good to know, to make sense. Use the previous knowledge here. That's the reason. All right, so what are we looking for? Let me point it out. We are looking for intervals and the points over which or at which f of x is bigger than or equal to 0. Okay, let's highlight. At what point, at what interval, the function is bigger than or equal to 0. Positive or 0. Use a very strong pink. Positive, this one. Positive, this one, this one. Okay. All right. So basically, this, oh, that idea. Basically, this, this is negative. Yeah, this one, this one, this one. So it is from net infinity to -7 closed union. This is 0, 0, 0. Union 0 to infinity. Okay, 0 to infinity. I hope you see it. Positive or 0. So from 0 all the way to infinity, the function is positive or 0. As you can see, at 0 is 0. From 0 to 3 is positive. At 3 is 0. From 3 to infinity to positive. So the whole thing can be combined as one interval, 0 to infinity. 0 is included. And another piece is net infinity to -7, -7 included. Do you agree, guys? The only, yeah, actually this makes probably better explain it. The only interval, the function is not bigger than or equal to 0 is that one. It's 97 to 0. We just need to get rid of that interval. The rest of the part on the domain, the function is positive or 0. So this is the solution. So this is the solution. All right. Do you agree, guys?
Yes.
Okay, very good. Feel free to ask a question. I can know. Maybe I can improve the design of the graph. The reason I put the zeros here, there's one way to design it, is when you go to calculus and you have to consider the turning point, the inflection point, you might need this design better. Okay, so those 3 questions showed us. Through those questions, I showed you how to solve polynomial inequalities using the sign chart method. Next, we are going to focus on solving the real rational inequalities. The denominator is not 1, is a polynomial. Okay, let's start this one. The standard form of a rational inequality has 0 on the right side. So it already has 0 on the right side. We don't have to worry about that. Since it's already in the standard form, we can let f of x be the left side. This time, the f of x is a rational function, x minus 5 over x squared minus 64. Rational function is a polynomial over polynomial. We still have to factor. Numerator is already prime, so what we can do is we can do x minus 5. I like to play this like that. So the numerator is a binomial, linear binomial, x minus 5. The denominator we can factor as x plus 8 times x minus 8. You see that, right? It's a special binomial. The denominator is a difference of 2 squares. X squared minus 64 is x squared minus 8 squared. So it's x plus 8 times x minus 8 is a formula. The formula. Okay, so we are going to consider the following critical points. Instead of saying roots, this time is not all roots. 5 is a root because 5 is a 0 because it will make the function equal 0. But we also have to consider the zeros in the bottom. So basically, we are going to consider the following points. We can call them critical because they're important, right? Points. Those critical points include the roots of the top and the roots of the bottom. Rational function is a polynomial in the numerator, a polynomial in the denominator. We're going to factor the numerator and the denominator, and then identify all the zeros, not only the zeros of the top, also the zeros of the bottom. So we have the opposites of those 3 numbers. I put them in red. So positive 5, negative 8, positive 8. And then in the real number line, anybody can tell me what's the domain, guys? What's the domain of the rational function? Yeah, my question here is what's the domain of the rational function? Let's say this is negative 8, this is 5, this is 8. What's the domain of the rational function? What's the domain of the rational function?
Infinity.
Not infinity. Is all real except negative 8 and a positive 8, right? The function is undefined at negative 8 and a positive 8. So the domain is all real except those 2 points, because those 2 points would make the denominator be 0, and that's not okay. All right, so I put a hole at negative 8 because the function, the rational function, f of x is undefined at negative 8. I also put a hole at 8 because the function is undefined at 8. Those details matter, okay? Those details matter. So 5 is fine. So the 3 critical values separate the domain into 3 parts. This interval, this 4 parts. Sorry, said it wrong. 4 parts. Interval negative infinity to negative a, negative a to 5, 5 to a to positive infinity. 4 intervals. And then we can start our chart. Our chart starts from the intervals. Negative infinity to negative 8. I would not put a negative 8 here like earlier. because the function is not well defined at negative a. So the function, the independent variable x of the function does not assume negative a. So no negative a. We can go from negative a to 5. You can put a 5 here, that's fine, that's fine. And from 5 to 8. And no 8 because 8 is not in the domain. And then from 8 to past infinity. Those details are actually is the challenging part. And the next row we are going to find a testing point for the intervals only, okay? For the intervals only. From negative infinity to negative a, I'll try negative 10. From negative a to positive 5, I'll do 0. From 5 to 8, that's a tricky one, right? From 5 to 8, which number is convenient? Either 6 or 7. Let's do 7. From a to infinity, we do 10, right? And now we are going to look at the value of the function at those intervals. We're going to write function in the factored form. In the top, we have x minus 5. In the bottom, we have x minus plus a times x minus a. Double check, that's the factored form of this rational function. When I say factored form means I factor the numerator, also the denominator, x minus 5 plus a minus a, okay. I'm going to highlight the color for the 3 parts. Blue is the top factor. Yellow is the x plus 8. Green is the x minus a. Okay. The rational function has 1, 0. So f of x equals 0 at 5. Not a negative a and a positive a. We don't even have them, right? From the very beginning, we know the 2 points, negative a, positive a, not even in the domain. So we don't consider them. And in the first interval, when we plug in negative 10, blue, negative. In the numerator, negative. Yellow, negative. Yeah, be very careful. Negative, negative. Green, also negative. So denominator, negative times negative become positive. Numerator is negative, denominator is positive, so the quotient is negative. All right? 0. 0 would make the blue negative. That's the top. We'll make the yellow positive. Would make the green negative. So positive times negative, the bottom is negative. The bottom is negative. Numerator is negative, bottom is negative, so positive. The quotient is positive. If you really struggle this, I think this is easier. But if you really struggle, what you can do is just plug in the value and then get the output, get the value of the function to see if it's positive or negative. Next, 7. 7 would make the blue positive in the numerator. 7 would make the yellow positive. 7 would make the green negative. As you can see, 3 things, right? In a quotient is going to be negative because positive times negative, the denominator now is negative. And numerator is a positive, denominator is negative, is going to be negative. Next. Testing point is 10. 10 will make the blue positive, yellow positive, green positive. Everything's positive, definitely is going to be positive. We are looking for intervals in which f of x over which f of x is bigger than 0, okay? Yeah, so the original inequality is f of x bigger than 0, strictly bigger than 0. So it means positive. We are looking for intervals over which f of x is positive cannot be 0. Has to be strictly positive, strictly bigger than 0. So let's see which one shows positive. We have this one positive. We have this one positive. All right. And that's it. So the solution is -8, 5, -8 from -8 to 5 open interval, union +a to +infinity. So that's the two intervals over which or in which the function is strictly bigger than 0. So that's the solution, okay? -a to 5 positive and a to infinity positive. This time we do not consider, this time the right endpoint is not bracket because at 5 the function equals 0, but we don't have a bigger than or equal to. We have a strictly bigger than. So we won't include the 5 in the solution. So it's open. All right, so that is a rational function, rational inequality. The process is very similar. Is when the only difference, kind of like the only difference is when we identify the critical points. They include the zeros of the numerator, also zeros of the denominator. Also, we know zeros in the denominator are not in the domain. So we have to consider the boundary, the endpoints of each interval. That is the different part. Any questions so far? If not, we continue practicing. This one is more complicated. Let's do this one. Okay. This rational inequality is already in the standard form because the right side is 0. We let f of x equals x squared minus 11x plus 24 all over x squared plus 18x plus 81. Can you tell me what are we going to do now?
Factor them both.
Yeah, factor both top and bottom. Very good. Numerator, x minus 3, x minus 8. -3, -8, multiply to 24 positive, add up to -11. Denominator, x plus 9, x plus 9. Is actually x plus 9 square. Actually, x plus 9 square. We can do the color, -3 here, -8 here, +9 here. So the critical points, the important points of the function are the opposites of the three red numbers, +3, +8, -9. Among which +3 and +8 are the zeros of the top. So also are the zeros of the rational function. The -9 is the zero of the bottom. So -9 is not in the domain of the function. -9 is not in the domain. So when you draw the real number line, 99 is here. You want to put a circle, a hole here to remind you 99 is not in the domain. 3 and 8, yes. Let's say 3 is here. 8 is here. Then the three numbers, the three values, critical values, will maybe call the three critical values or critical points. Divide the whole real number line. Divide the domain into 3 parts. First part, second part, 4 parts. I'm sorry, 4 parts. 1, 2, 3, 4. Okay, 4 intervals. Then we can do the chart. X from net infinity to -9, open. Okay, open. -9 is not in the domain, so forget about it. And then from -9 to 3. 3 is in the domain, is a 0. We can put it here. It really depends on how you design the chart. 3 to 8, from 3 to 8, and h is also a 0, and from a to infinity. So that's the first row. And you need to make sure the union of all of those gives the domain. The domain for this question, for this problem, is all real except -9. So everything except -9. So we have net infinity to -9, -9 excluded. From -9 to 3, -9 excluded, 3 is excluded, but we have 3 here, and 3 to 8, and 8 here, 8 to infinity. So everything except -9. So that, yeah, that's how we separate, divide the domain of the function. Next, we do testing point. Net infinity to -9, let's do -10. -9 to 3, let's do 0. 3 to 8, do 5. 8 to infinity, positive 10. Next row, we are going to write the function, rational function f. F of x in the factored form. It is -3 minus a. X minus 3 times x minus 8 over x plus 9 to the power of 2. Double check. It is x minus 3 times x minus 8 in the numerator, x plus 9 to the power of 2 in the denominator. Okay. All right. I'm going to highlight the factored form of the function as, I'm trying to get a blue. Okay. Blue times yellow. And on the bottom, let's do green. Knowing green has a square, so the denominator always positive. The green, on the bottom always positive because it's a perfect square, because it's second power. Let's see the sign of the function when x assumes -10. -10 will make the blue negative. Will make the yellow negative. So negative times negative. Will make the bottom positive because bottom always positive, right? So bottom is always positive. Numerator, negative times negative is positive. And next we do 0. 0 would make the blue negative. Yeah. 0 would make the blue negative. Would make the yellow negative. Will make the green positive. So still positive. Still positive. And next 3, at 3 the function equals 0, right? That's a 0. At 5 make the blue positive, yellow negative, green still positive because it's square, always positive. So numerator is negative, denominator is positive, so negative here. At a we have 0. And at 10 will make the blue positive, will make the yellow positive, will make the green positive, so everything is positive. And what are we looking for? We are looking for intervals in which the function less than 0. Okay, this is time to like recall the purpose. The purpose is to find. We were looking for intervals in which f of x less than 0. F of x less than 0. Okay, so it means negative. We are looking for negative. Okay, we are looking for negative. Look at the last row. Positive, no. Positive, 0. This is the only negative, right? This is the only negative. From 3 to 8, that is the only negative. 0 is not. 0 doesn't work. Positive doesn't work. Only negative works. So the solution is an open interval from 3 to 8. If you graph the rational function on the left side, you can see the graph of the rational function on the left side is below the x-axis from 3 to 8. And all other parts, all other branches or parts are above the x-axis. All right, guys? At -9, you know, the function has a vertical asymptote, if you want to know. The function has a vertical asymptote. But either way, it's not defined. It's not defined. It's possible, you know, it's like this. Like this is -9. It's -9. This is the vertical asymptote, and the graph, you know, like that, you know. So from -infinity to -9, positive, above x-axis. From -9 to 3 is also, maybe this is 3, also above x-axis, right? Yeah, maybe it's not like that. But I'm just showing you, you can look at the graph and make sense of the result. Will be very cool. Let's continue, practice more. This one we need to talk about. This problem is necessary to include a problem like that because this given rational function is not in a standard form. A common mistake is that f of x equals the left side, but they forgot the very first step of solving a rational inequality is to write the inequality in standard form. This one is not yet in the standard form, so we need to spend time to do that. Okay? So 4x over 3 minus x is bigger than or equal to 4x. Some of you, okay, like me, I feel uncomfortable for 3 minus x. So I might do something to write x minus 3, but it's just an option. You don't have to. Yeah, if we do not do nothing about that, that's still okay, okay? So 4x over 3 minus x minus, we're gonna minus 4x from each side. Then the right side now is 0. The left side is 4x over 3 minus x minus 4x. And you have to write the left side as a rational function, which is a polynomial over polynomial. So to do that, 4x over 3 minus x minus, we can write 4x as 4x times 3 minus x over 3 minus x. If you cancel 3 minus x, you have 4x, right? You go back. And now the two rational expressions on the left side have the same denominators. We can, just like adding two fractions, you need them have the same denominator. So when you're adding two rational expressions, you also require the two rational expressions have the same denominators. Now they do have the same denominator, 3 minus x. We can write a denominator and solve the top, which is 4x minus 4x times 3 minus x bigger than or equal to 0. And then we have to simplify the left side, okay? I can do the simplification here. 4x minus, well, let's distribute to remove the parentheses. Negative 4x times 3, negative 12x. 4x minus 12x. And then plus 4x squared. Let's see. double check, 4x minus 12x plus 4x squared. And 4x minus 12x is a negative 8x and 4x squared. 4x squared minus 8x. So that is the top. 4x squared minus 8x. Denominator is 3 minus x. As I said, is okay. You keep 3 minus x like that is totally fine. There's an option you can do 4x squared minus 8x over x minus 3. Like you multiply -1 here and then you flip the inequality symbol. But if that's too much, just forget it. Okay? I don't want you to do extra and mess it up. This is totally fine. So we can let f of x be the left side. So now the left side is a rational function. Look, right? A rational function also look like a rational function. Numerator is a polynomial, denominator is a polynomial. And we let the left side as 4x squared. We let the f of x be the left side, which is 4x squared minus 8x over 3 minus x. Since the denominator is so simple, we don't really have to do that. Or if you really want, we can do this, right? The thing is, 3 is the 0 of the bottom. Should be easy to tell, right? Or you can just leave it here. And the numerator, let's factor 4x out, because that's the GCF of the binomial. 4a, GCF is 4, x squared x, GCF is x. Factor 4x out, we have x minus 2. Double check, 4x times x, 4x squared, 4x times -2, -8x. Okay, so now we have the left side factored. And now let's identify the critical value or critical points. 0 is 1, right? 2 is another, and 3. Do you agree, guys? The numerator has 2 roots. They are 0 and positive 2. The bottom has 1 root, which is 3. Since the bottom has a 0, 3, the function is not defined at 3. So when you draw the real number line, when you draw the domain, you have to have a circle at 3. Indicate 3 is not in the domain. 0, yes. 2, yes. So the 3 critical values divide the whole domain into 3 parts, 3 intervals. 4 intervals, sorry. 1, 2, 3, 4. 4 intervals. And let's make the chart now. The upfront work is kind of like a one question, right? One big question. But you have to write the rational inequality in the standard form. You have to make the right side be 0. That's the way to do it. Even it's might be challenging for some of you. It is very important. First row, the domain, and divided into parts, right? From -infinity to 0, and 0 is a 0. From 0 to 2, 2 is also is in the domain. From 2 to 3, 3 is not in the domain. And then from 3 infinity. Let me double check. Then infinity to 0, 0, 0 to 2, 2, 2 to 3, 3 is not in the domain. 3 to infinity. Okay, so looks good. Testing point. Then infinity to 0. Let's try -1 or -10. Really depends on your preference. We can try -1. 0 to 2, +1. 2 to 3. Unfortunately, we have no choice. We have to do a decimal. 2 to 3, between 2 and 3. I mean, from 2 to 3, that open interval. We have to find a decimal to be the testing point, because the end point will not be able to be the testing point. 2.5 is not too bad, you will see. From 3 to infinity, we can do 10. Each single detail have to be very accurate to guarantee the result is correct. So the last row is going to be f of x in the factored form. In the factored form, 4x, x minus 2. 4x, x minus 2. Denominator. 4x, x minus 2. Denominator 3 minus x. 3 minus x. When you color the three parts, be very careful, okay? The first part is supposed to be blue. I want it to be blue. Is a 4x. 4 is a positive number, so it doesn't affect if you don't include it. But sometimes if this part is possible to be negative, then you need to be very careful. All right, so 4x is the blue. By blue cover 4x. By yellow cover x minus 2 in the parentheses. My green is 3 minus x on the bottom. Let's see the sign. Let's plug in -1. -1 make the blue negative. Make the yellow negative. Make the green, okay, you tell me. Make the green positive or negative? Guys.
Positive.
Yes. If you are not sure, just use your calculator. So that's a disadvantage when you have a factor that's not in a standard form. So when you plug in, it might be not very convenient. But not too bad. You plug in -1. 3 minus -1 is going to be positive. So negative times negative is positive, so positive here. At 0 is 0. At 1, now let's plug in 1. 1 would make the blue positive, make the yellow negative, make the green positive. 3 minus 1 is positive, right? So negative. At 2, 0. 2.5. 2.5 will make the blue positive, would make the yellow positive. Yeah, 2.5 is bigger than 2, so 2.5 minus 2 is positive. We'll make the green also positive. 2.5 is less than 3, so if we use 3 to minus 2.5, we're going to positive. So positive, everything is positive. And let's plug in 10. 10 will make the blue positive. We'll make the yellow positive. Would make the green negative, right? 3 minus 10, -7, negative. So positive numerator, negative denominator is negative. Okay. So we complete the chart. And what are we doing here? We are trying to find the intervals or points such that the function, now you do not look at here. Now you're going to look at, here. After you write the function in the standard form, okay? After you write the function, the inequality in the standard form. So that's what you're looking at. So you are looking for intervals such that f of x bigger than or equal to 0. So 0 is fine, positive is fine, but negative is not fine. Let's see. Positive is fine. Okay, this column positive, so it's fine. 0 is fine, so include 0. Negative, no, we don't include that. 0, yes. Positive, yes. And that's it. So we are looking for the columns, and we have a positive or 0. So this one, this one, this one, this one, and that's it. Okay. So let's combine the two intervals. So the solution from net infinity to 0 with 0 included, so closed. Union from 2 to infinity, from 2 to 3. Oh my God, I almost read it wrong. From 2 to 3 only. From 2 to 3, but with 2 included. So 2, at 2, we have a bracket, left-handed bracket. So left close, right open. You cannot have 3 closed because 3 is not even in the domain. So be very careful with the detail. And that's the solution set of the original given rational inequality in the interval notation. Details matters. All right, guys, that's everything for today. I think I covered most of the questions I prepared. Yeah. I recorded the class. If it helps, you can rewatch the video. Today is Thursday. Next Tuesday we review, and then we arrange Unit 3 test. And next Thursday we are going to start Unit 4. Feel free to email me if you have any questions. You guys have a good week, and I'll see you on Tuesday. You have a question?
Yes, Professor. It's
Yeah.
about the midterm.
Let me stop the recording. Let me stop the recording. Pause recording. Stop recording. Okay. Yes.
It's about the midterm review. I retake the review. So the question is, if I want to go retake the midterm test, is